Okay, we're going to brute force this presentation. I've got a camera in front of my computer. Hopefully it'll work out okay. This is section 14.4. Remember our tuning fork. As the tines of a tuning fork move back and forth through the air, they exert a force on a layer of air and cause it to move. In other words, the tines do work on the layer of air. Energy is lost in the form of sound and also friction as the tines bend. So the vibration of the fork slowly dies out. The average intensity I of a wave on a given surface is defined as the rate at which energy flows through the surface, delta E over delta T, divided by the surface area. The direction of energy flow is perpendicular to the surface at every point. The rate of energy transfer is power. So we can write this in another way, where P is the sound power passing through the surface measured in watts. At a frequency of 1,000 hertz, the faintest sounds the human ear can detect have an intensity of about 1 times 10 to the minus 12 watts per meter squared. This intensity is called the threshold of hearing. The loudest sounds we humans can tolerate have an intensity of about 1 watt per meter squared, the threshold of pain. Alright, at the threshold of hearing, the increase in pressure in the ear is approximately 3 times 10 to the minus 5th pascals over normal atmospheric pressure. Because atmospheric pressure is about 1 times 10 to the 5th pascals, this means the ear can detect pressure fluctuations as small as about 3 parts in 10 to the 10. The maximum displacement of an air molecule at the threshold of hearing is about 1 times 10 to the minus 11 1 times 10 to the 11 meters, a remarkably small number. If we compare this displacement with the diameter of a molecule, which is about 10 to the minus 10 meters, we see that the ear is an extremely sensitive detector of sound waves. The loudest sounds the human ear can tolerate at 1 kilohertz correspond to a pressure variation of about 29 pascals away from normal atmospheric pressure, with a maximum displacement of air molecules of 1 times 10 to the 5th meters. It seems the loudest tolerable sounds have intensities about 1 times 10 to the 12 times greater than the faintest detectable sounds. That being said, we don't perceive the most intense sound as being 10 to the 12th times louder than the faintest sound, because the sensation of loudness is approximately logarithmic in the human ear. The relative intensity of a sound is called the intensity level, or decibel level, defined by the equation shown. The constant I.O. is the reference intensity, the sound intensity at the threshold of hearing. I is the intensity, and beta is the corresponding intensity level measured in decibels, dB. The word decibel, which is 1/10 of a bell, comes from the name of the inventor of the telephone, Alexander Graham Bell, who lived from 1847 to 1822. Let's get a feel for various decibel levels. First, let's substitute the threshold of hearing intensity. From this result, we see that the lower threshold of human hearing has been chosen to be 0 on the decibel scale. Let's continue increasing the intensity by powers of 10. Notice the pattern. Multiplying a given intensity by 10 adds 10 dB to the intensity level. This pattern holds throughout the decibel scale. For example, a 50 dB sound is 10 times as intense as a 40 dB sound, whereas a 60 dB sound is 100 times as intense as a 40 dB sound. On this scale, the threshold of pain, I equals 1.0 watts per meter squared, it corresponds to an intensity of 120 decibels. Jet airplanes can create intensity levels of 150 dB, and subways and riveting machines have levels of 90 to 100 dB. If you are exposed to intensity levels this high, your ears can be seriously damaged. It's a good idea to wear earplugs whenever you will be exposed to intensity levels greater than 90 dB. Recent evidence suggests that noise pollution, which is common in most large cities and in some industrial environments, have been a contributing factor to high blood pressure, anxiety, and nervousness. According to federal OSHA regulations, no office or factory worker can be exposed to noise levels that average more than 85 dB over an 8-hour day. Imagine a factory filled with noisy machines. Let's say one machine produces a noise level of 70 dB. Because of the logarithmic nature of intensity levels, adding a second machine doubles the noise level by only 3 dB. This table gives the approximate intensity levels of different sounds. You can see a nearby jet plane 150 dB, jackhammer, a machine gun 130 dB, a siren, a rock concert 120 dB, subway, power mower 100 dB, busy traffic is 80, vacuum cleaner 70, normal conversations about 50 dB, a mosquito buzzing is 40 dB, we get a lot of them here in South Texas, a whisper is 30 dB, rustling leaves 10, and the threshold of hearing is 0. And that's it for this section. The next section will be 14.5.